Hey everyone, this is a video to cover all of the material on acids and bases that are at the end of chapter 6. So to begin with, we need to know what is a Bronsted-Lowry acid, and the answer is that Bronsted-Lowry acids are proton donors, and we'll see some examples of those in just a second. And then the corollary is the question, what is a Bronsted-Lowry base? And the answer is they accept protons, and you remember this from Gen Chem. All right, so let's look at some examples of Bronsted-Lowry acids and bases in a reaction. So here's hydrochloric acid, a classic strong acid that you remember. It's a Bronsted-Lowry acid, and that's because it has H plus in the formula that it can donate. Here's a Bronsted-Lowry base, NH3, and it's got a lone pair, which is a really good spot to accept a proton. And when they react, the HCl donates that proton, which is then accepted on the lone pair of the NH3, and we end up with Cl minus, the resulting species after the proton has been donated, and NH4 plus, which is what results after it's accepted the proton. All right, we have some other terminology that's really important that we can see here in this example. We see that HCl is connected with Cl minus, right? And the way that they're connected is they're called conjugate acid-base pairs. So we would say Cl minus is the conjugate base of HCl. And we would also say NH4 plus is the conjugate acid of NH3. And we could go backwards, and we could say that in the case of the HCl Cl minus conjugate base acid-base pair, we could say the HCl is the conjugate acid to chloride, and we could say NH3 is the conjugate base of NH4 plus. So what's really important in this kind of a situation is to be able to identify conjugate acid-base pairs. And the thing to keep in mind is that conjugate acid-base pairs are only different from each other by an H and one electrical charge unit. So in other words, they simply differ from each other by H plus. And so we'll see that in the next page as we do some example conjugate acid-base pairs. So here's a little table you can make, and we'll fill it in to practice. So for example, if we said that H2O is the conjugate acid to something, and the question is, what is its conjugate base? What we do is we have H2O donate H plus. That means it's lost H and it's lost a positive charge. So we go from H2O to OH, and then we go from an electrically neutral thing to minus. So that's how we would think about that. Let's say instead we're talking about the hydrogen carbonate ion, or bicarbonate as it's called. If that's a conjugate base, then we have to add H to it, and we have to up its electrical charge by 1. And you can see that we end up with H2CO3 neutral. If we go try dihydrogen phosphate, all right, we've got 2 H's, and we have a negative charge. We're going to add H, we're going to subtract H, and we're going to lower the charge by 1 if we go to do the conjugate base. And so we'd end up with HPO4 2 minus. We can actually take that very first example, the water example. We can make water the conjugate base and see what would happen if we added H plus to it, and we end up with H3O plus, right? We can think about maybe something like that H2PO4 that we saw before. We can see that that species is also able to accept a proton. So what would it become if H2PO4 minus accepted a proton? Well, we'd have H3 PO4 neutral. So one thing you can see in all of this, in the case of water, for example, H2PO4 minus. In the case of let's see, in the case even of HCO3 minus, which we didn't do, some of these acid-base species can act as both an acid and a base, and we say that they're amphoteric. So they can both donate and accept H+. And that's a good vocabulary word to know. Another thing to think about with regard to acids and bases is that we see everything seems to be focused on H+, and in aqueous solution, so in other words, if water is the solvent, really, to be technically correct, H+ does not exist. But we will pretend that it does, because it makes writing all of our chemical equations so much easier. So how does H+ actually really exist in solution? In other words, what is an acidic solution really like? And the answer is that H+ immediately gloms onto the one of the two lone pairs in water. So if H+ is donated to water, it goes right onto one of those lone pairs, and then we end up with H3O+. All right, but even H3O+ doesn't exactly exist in solution because it's going to be really positive in each one of those three H's, and so we can show that species kind of like this if we make a little dash wedge drawing. All right, here's the remaining lone pair that's on H3O+. That whole thing, by the way, is positive charge, and we'll show that in just a second. But on each one of those hydrogens, there's a lot of partial positive charge, and as a result, they're going to attract neighboring water molecules really tightly. And I'm not showing the lone pairs on the waters that I'm drawing in right now, but the bottom line is those O's are very negative. They're going to be attracted to the positive H's, and we end up really with a species that isn't exactly H3O+ or H+. Really effectively, water is existing in something like this with a positive charge. It really is kind of like it's H9O4+. So the lesson here is that we're going to pretend like that's really just H+, because it's really hard to do chemical reactions with things like H9O4+, if that's how the H+ is really acting. So we're going to actually just abbreviate everything H+ whenever water has accepted a proton, but we're going to just be aware that it's a little bit more complicated than that. All right, one thing to consider is that if water is the solvent, then it's going to be the primary species that mediates the H+ being donated and accepted. So we have to think about liquid water and the fact that it really exists in chemical equilibrium with H+ and OH- because the water, as you might remember from Gen Chem, can undergo what's called autoprotolysis. Some of your Gen Chem textbooks call this self-ionization or auto-ionization. But you can see, since this is an equilibrium, we must have an equilibrium constant and an equilibrium expression, which looks like this. The value for Kw is about 1 times 10 to the minus 14th at 25 degrees C. All right. We find that if we change the temperature, just like for any equilibrium constant for any reaction, if we change the temperature, Kw changes. And so when you study it, you find out that as temperature goes up, Kw goes up. And you should be able to reason out from your understanding of chemical equilibrium that if the temperature increase causes an equilibrium constant to increase, that must mean that delta H for autoprotolysis is negative. In other words, this reaction that we see up here is really an exothermic reaction, and we can discover that by simply looking up the Kw values at different temperatures, and we would see that as temperature goes up, Kw goes up. At 37 degrees C, for example, that's body temperature. Kw is not 1 times 10 to the minus 14th. Kw is about 2 times 10 to the minus 14th. So it's literally twice as big if we just raise the temperature by 12 degrees to body temperature. All right, another thing that we need to think about is that because there's an equilibrium expression that we can write that's always true at whatever temperature we're operating at, for us it's always going to be 25 degrees C. So we're going to always use the 1.0 times 10 to the minus 14th number. If that's true, then what you can see is if we know either one of those two concentrations, H plus or OH minus, we can calculate the other just by substitution. So as an example, if H plus is 1.0 times 10 to the minus 11th molar, calculate the OH minus concentration, and you can do this on your calculators, or you should be able to do it in your heads, but you'll find that OH minus is simply going to be the value for Kw, 1 times 10 to the minus 14th, divided by 1.0 times 10 to the minus 11th, and we end up getting 1.0 times 10 to the minus 3rd for our hydroxide concentration. And we can do a similar thing to calculate H plus if we knew OH minus. All right, then what comes out of all of this information is that we have a system for talking about the relative acidity of an aqueous solution, and that measurement tool is called the pH. We define pH, as you already know, as the negative of the log of the H plus concentration. All right, and we can make a similar formula that says instead of calculate pH from H plus, we can calculate H plus if we know the pH, and that's simply going to be 10 to the minus pH. So we can calculate either one from the other, and you should be able to do calculations like this. If H plus is 1 times 10 to the minus 4th molar, what's the pH? And you ask yourself, all right, I'm going to take the log of 10 to the minus 4th, and you're asking yourself, to what power do I have to raise 10 to get 10 to the minus 4th? And the answer, of course, is minus 4. So then we take the negative of that value, and that gives us a pH of 4. And if the number that was given to begin with has two significant figures, that will be written with those two significant figures to the right of the decimal point. So that pH 4 is written just like that. If we have a hydroxide concentration that's known, 1.0, for example, times 10 to the minus 8th molar, then you can convert that to H plus, and you can do the math in your head, or you can use your calculator, but you'll get 1.0 times 10 to the minus 6th molar. And then we ask ourselves, to what power do we have to raise 10 to get 10 to the minus 6th? And the answer is 6. And we take the negative, and we'll see that the pH in this particular last situation ends up being 6. Okay. All right, and then all that should be just a super easy review from your Gen Chem class. Another question we need to ask ourselves is, for specific kinds of acids, we call them strong, and for other kinds of acids, we call them weak. So it's important first to know what makes a strong acid strong. And the answer is that a strong acid, they're strong electrolytes, and that means that they're fully or nearly fully dissociated in aqueous solution. And so as an example, if we study a strong acid that you remember from Gen Chem, if we have an aqueous HCl solution, and we understand that HCl undergoes chemical equilibrium with its dissociation products, H plus and Cl minus, and we look up the equilibrium constant for that reaction, okay, we find that we abbreviate that equilibrium constant Ka because this is an acid dissociation, and that numerical value is about 10 to the 6th. It's an enormous number. And so if we have a solution with a formal concentration of HCl of 1 molar, that is to say, without regard for any chemical reactions that might occur or changes to the HCl that happen to it once it dissolves, we have a 1 molar or a 1 formal concentration of HCl. What we find is that the actual concentration of aqueous dissolved HCl is very, very small. And what is actually very close to 1 molar is the concentration of H plus and the concentration of Cl minus. So to summarize, if an acid is strong, that means that it's essentially completely dissociated, like sodium chloride would be, or another strong electrolyte. Okay, so because of this equilibrium being so product favored, it's a really good approximation for strong acids to write. Instead of the double equilibrium arrow, which is correct, we approximate that complete dissociation by saying that there's just a single arrow there. Strong bases are similar. We assume that they're either fully or nearly fully dissociated. So they're also strong electrolytes. And, an example might be something like NaOH. So in solution, if NaOH is dissolved, we would approximate the full dissociation by simply saying it's going to exist either completely or nearly completely as Na plus and OH minus fully dissociated. So what you guys have to remember is that you need to know and memorize the list of strong acids. And there are about several hundred, 200 or 300 actual total acids in the chemical universe. And if you memorize the 7 that are strong, you'll have a way to memorize, therefore, or to know and recognize whether any acid is strong or weak. If an acid is one of the 7 strong ones, then you recognize it. If it's not in the list of strong ones, then it therefore must be weak. So I'm going to give you the list of the strong acids. To memorize. And they are HCl, HBr, HI, then HNO3, nitric acid, HClO3, that's chloric acid, HClO4, that's perchloric acid, and then a special case H2SO4 sulfuric acid, but that is a strong acid only for the donation of the first H plus from it. It can donate 2, and we'll learn in a little bit that that means it's a diprotic species, but it's only strong for the donation of the first one. All right. Those are the strong acids that you need to memorize. You need to memorize also what are the strong bases. And so our strong bases really come in a couple, 3 different categories. The group 1 in the periodic table, that's the alkali metals, the group 1 hydroxides. And so some examples would be LiOH, NaOH, KOH, etc. The second group of strong bases to memorize are basically just one chemical that's in the category group 2 hydroxides. And I'm just going to make that singular because there's only one of them that actually acts like a strong base, and that's barium hydroxide. And you can see that it's got the possibility to create two hydroxides in solution. So keep that in mind. And then the third category are what I'm going to call QA hydroxides. And the QA stands for quaternary ammonium hydroxides. There's another M in there, just a minute. And so an example, like the abbreviation that you would use in OChem would be something like this: R4N plus OH minus. And so the quaternary ammonium hydroxides are going to be things like this. So because the N has 4 bonds, it's going to be positively charged. And when that cation, that tetramethyl amine cation, is connected to an OH minus, simply by electrostatic attraction of the OH minus to the tetramethyl amine there, that gives us quaternary ammonium hydroxide. And there are a large number of these things where all you do is simply change the R groups that are attached to the N. All right, so with regard to the strong acid and base pH calculations, they're typically pretty easy. So let's say we have an HNO3 solution. It's a strong acid with a formal concentration of 0.0463 molar. We want to know what is the pH. And so what we first consider is that the H plus concentration is equal to, therefore, the formal concentration of HNO3, right? In other words, the H plus concentration is therefore 0.0463 molar. And if that's the H plus concentration, we can easily calculate the pH. And so we simply take the negative log of 0.0463, and we get that pH 1.334. Similarly, if we have a KOH solution with a formal concentration of 1.3 times 10 to the minus 3 molar, then what we really know is that in this solution, the hydroxide concentration is equal to that formal concentration of 1.3 times 10 to the minus 3 molar. We can then get our H plus concentration, and we can calculate pH, and I'll leave that to you. But the pH you should get when you calculate the value should end up being 11.11. And if that doesn't make sense, just do a quick pause, turn your hydroxide concentration into an H plus concentration using Kw, and then from the H plus concentration, calculate your pH. You get kind of an interesting problem when you have to deal with the one weird strong species, that is barium hydroxide. So let's just do a quick little problem with barium hydroxide to show you how you'll deal with that. Let's say you have a barium hydroxide solution with a pH of 12.586. So what we want to know is let's calculate the formal concentration. So the first thing we have to do is take our pH and convert it into the H plus concentration. So we know that H plus is 10 to the minus 12.586, 10 to the minus pH, and we get the value, giving ourselves a couple of extra digits, 2.594 times 10 to the minus 13th. And we can calculate hydroxide using the Kw. So the Kw divided by that H plus concentration gives us hydroxide 0.0385 molar. All right, but we know that that hydroxide is going to come from the fact that barium hydroxide can create two of them. So we can do a little quick unit conversion calculation to say 0.0385 moles of hydroxide per liter of solution. Then we know that we make 2 moles of hydroxide for every 1 mole of barium hydroxide. And therefore, the actual formal concentration of barium hydroxide that had the pH of 12.586 is really 0.0193 molar. And there's our answer to the question. All right, those are some things to remember from Gen Chem about strong acids and strong bases. What we need to think about next are weak acids and bases. And they don't dissociate or ionize completely. So unlike the strong species that ionize completely or dissociate completely, the weak acids and bases don't. So here's an example. HF is a weak acid. And so when we write its equilibrium reaction that creates H plus and F minus, the important thing to recognize is nearly all of the HF that's dissolved is still HF. And the way we know that nearly all of the HF is still in the HF molecular form is that the Ka for HF is really small. It's 6.8 times 10 to the minus fourth. If we think about a weak base example, that's kind of the same thing. Weak bases don't dissociate in the same way that weak acids do. They undergo a process we call hydrolysis. So for the weak base to actually act as a base, it has to accept a proton from someone, and that someone is going to be water. So weak bases cause water to break up. That is, they hydrolyze water, and we end up with the conjugate acid NH4 plus, and then we end up with the hydroxide that makes NH3 act as a base. And here, most of the NH3 that would be dissolved in water would still exist as NH3, and we know that because Kb is relatively small. All right, and we have, like I said, some names for the Ka and the Kb. And so the Ka is called an acid dissociation constant, and Kb's are called base hydrolysis constants. All right, so when we think about the value of the Ka, we think about that the same way we think about, for example, the H plus concentration and pH. We can take the Ka and we can calculate something called the pKa simply by doing that negative log operation on it. So pH is the negative log of H plus, pKa is the negative log of the Ka. And if you study values for Kas and pKas, what you can do is make yourself a little table that looks something like this. Let's say you have a Ka and you want to know what its pKa is. You can kind of see the trend. And so using nice round numbers that are perfect powers of 10, you have something like this. If you have a Ka of 10 to the minus 2, the pKa ends up being 2. 10 to the minus 3, the pKa ends up being 3. pKa, or Ka, I should say, of 10 to the minus 9th, the pKa would be 9. And what you see is that as we go from 10 to the minus 2 to 10 to the minus 9th, these are all Ka values that are getting smaller. Whereas as we go and study the trend in the pKa's that correspond to each of those Ka's, we see they're getting bigger. And then we can write a nice little summary statement that as Ka goes down, the acid strength is going down. Since Ka measures how strong an acid is in terms of how much it dissociates, smaller Ka values mean that an acid is weaker, it dissociates less, and therefore we can write the second statement as Ka goes down, our pKa, which measures the exact same thing, must be going up. Therefore, strong, let's just say strongish weak acids have larger Ka and smaller pKa's. All right, and weaker weak acids have the opposite. They have smaller Ka values and bigger pKa's. So we can do a little test to make sure that you understand all of that. I can give you fake acid HA and fake acid HB, and I can tell you that fake acid HA has a Ka of 1.8 times 10 to the minus 5th. HB has a Ka of 4.6 times 10 to the minus 6th, and we can say which one is stronger. And the answer is this one. All right, so then we can do another kind of a quick little test. Let's say that we have fake acid HC versus fake acid HD. And instead of knowing Ka's, we know pKa's. All right, which one is the stronger one? One with the smaller pKa. Finally, if we wanted to compare a couple of last acids, let's call them HX and HY, and we know that a 0.1 molar solution of HX has a pH of 5.2, whereas a 0.1 molar solution, same concentration, same formal concentration of HY has a pH of 8.8. What we can reason out logically is that acid HX must be more dissociated because it produces more H plus and gives us a lower pH. Acid HY must be less dissociated, therefore it's got to be weaker. So our stronger of the two acids is the one that makes the more acidic solution. All right, we got some common solutes that you can put in water that will make the solution acidic, so we're going to call them common weak acids. And so some classic examples of common weak acids are carboxylic acids from OChem, so things like this one. They have these formulas, all right, or more generically, where R represents just a big piece of the organic molecule, and they dissociate like you'd expect. All right, another classic category of weak acids are non-metal hydroxides. I'm sorry, what am I saying? Non-metal oxides is what I meant to say. And so some examples of some non-metal oxides are things like carbon dioxide, CO2. That's a non-metal, C, and it's the oxide of that non-metal. Carbon dioxide. Some other ones are sulfur dioxide, sulfur trioxide, nitrogen monoxide, nitrogen dioxide, etc. So take a non-metal, add a bunch of oxygen to it and nothing else, and you have a species that when it goes in water will make the solution acidic. And here's an example with CO2. So aqueous CO2 will simply react with water, just like SO2 will react with water, and SO3 would react with water, etc. So CO2 interacts with water, and we end up undergoing chemical equilibrium where the water essentially breaks apart and then changes the nature of CO2, and we end up with HCO3 minus. We end up with the bicarbonate ion, and then we end up with H plus. And if you calculate, count up all the atoms and all the charges, you'll see that that works fine. And we would do something like, let's say SO3 would interact in an analogous way. And we end up with, I'm sorry, whoops, that would be HSO4. So that would be hydrogen sulfate ion plus H plus. There's one other category of common weak acids. And so our third bullet point under the common weak acids are metal cations with high charge. And so we'll study this later on in the semester, but a good example is something like iron 3 plus. And when iron 3 plus is dissolved in water, what happens is iron, the metal, causes hydrolysis of the water, where what happens is actually the OH part of water sticks to the iron as OH minus, so you have FeOH now, and since it was OH minus that stuck onto the iron, the negative charge on the hydroxide that sticks to the ion causes this charge to go down by 1, and we end up with FeOH2 plus, and then the remainder is H plus. And if you, again, count up all the atoms and the charges, you'll see that that's perfectly balanced. So we have a whole bunch of species like Fe3 plus that will make a solution acidic. Here's one more just for the fun of it. Here's nickel 2 plus reacting with water. All right, you take your nickel and you add OH to it, and then you pull its charge down by 1. And that's how the nickel ion would act as an acid in solution. Both of those two species, Fe3 plus and Ni2 plus, will make the solution measurably. Finally, then, in the category of these common weak species, common weak bases, are things basically that are organic amines and other nitrogenated organic compounds. And so as an example, here's methylamine. On that N is a lone pair, which is a great spot to accept a proton. And so just like ammonia, the CH3NH2 can take a proton on that lone pair from water. And we end up with CH3NH3 plus. That's the conjugate acid to methylamine, CH3NH2. And then the remainder is OH minus. And you can see how, therefore, the amine compounds like that can make the solution basic by creating OH minus. Here's a fun one. And for most of you who've had organic chemistry, you'll understand the line angle drawing. And that species is what we know as meth. But you can see it's got a nitrogen. It's a nitrogenated organic compound. It's actually technically an amine. And that thing, when it reacts with water, will make what you can probably bet. So we end up with the amine functionality protonated, and then the water molecule has produced hydroxide. All right, one final thing to think about is how it is that Ka and Kb are related to each other when we think about a conjugate acid-base pair. So if we think about formic acid, it's a weak acid, which is not in our list of strong acids. And if we write the acid dissociation reaction, we have this. All right, and that reaction would be described by some Ka. But if we take a look and we see this is the HCO2H, the formic acid, that's the conjugate acid in the conjugate acid-base pair. Its conjugate base is CO2 H minus, and when we think about it as a conjugate base, well, it should be able to undergo a regular old base hydrolysis reaction like this, CO2H minus, reacting with water, should make the conjugate acid again, and some hydroxide, and that reaction would be described by some Kb. What we find is that if we add those two reactions together, like we did when we covered the basics of Gen-chem equilibrium, what we see is that the conjugate base on the right in the first reaction and the conjugate base as a reactant in the second reaction cancel, the formic acid cancels, and we end up with simply water makes H plus and OH minus. And we know that when we add reactions together, we multiply their Ks, so the new K for this reaction would be simply Ka times Kb, but we also already know the K for this water reaction, it's Kw. And so what we see is always true is that the Ka for the weak acid in a conjugate acid-base pair times the Kb for its conjugate base will always give you the Kw. So that's true for any conjugate acid-base pair. All right. Final thing we can think about then are polyprotic species, and you may vaguely remember that we covered these in hardly any detail in Gen Chem, but if we look at something like malonic acid, its formula is H2C3H2O4. What you see is that it's got two leading protons that can be donated, so it's what we call diprotic species. Sometimes you have weak acids or weak bases that are triprotic or tetraprotic. This malonic acid species can undergo two successive dissociations. All right, and they look like this. And because the malonic acid can have two equilibrium reactions where it donates two successive protons, instead of just calling both of these Ka, we call the first one the donation of the first proton Ka1 and the equilibrium constant for the second reaction Ka2. And just like we could do with the simple monoprotic weak acids, you can take each of these two conjugate bases and you can show how they in turn would hydrolyze with water, so they can act as bases. So let's take the most basic species, the one that has the ability to accept the most protons, that's the C3H2O4 2 minus, and let's just write the two base hydrolysis reactions. And let's call the acceptances of the first proton equilibrium constant, abbreviated by Kb1. And then let's take the product, the amphoteric species that's intermediate, HC3H2O4 minus, and let's react that with another water molecule to get the fully protonated form. And the equilibrium is going to be described by Kb2. And for our diprotic species, we see that we have 2 Kas and 2 Kbs, and we want to know how they're related to each other to give us Kw. And if you study this for a little while, you'll see that Kw is always going to be Ka1 times Kb2, and Kaw would also be Ka2 times Kb1. And that's because if you number these reactions, where 1 and 2 are acid dissociation reactions and 3 and 4 are base hydrolysis reactions, you can see that reaction number 1 has the conjugate acid base pair H2C3H2O4 and HC3H2O4 minus, and we find that same pair in the bottom reaction number 4. And because those two species are present in reaction 1 and reaction 4, the reactions that are abbreviated by Ka1 and Kb2, when we add number 1 to number 4, we're going to end up with Kw. And we can see that same kind of a thing with the second pair, that is the HC3H2O4 minus, and then the fully deprotonated form C3H2O4 2 minus. Those two species that are present in reaction 2 are also seen in reaction 3. And so Ka2 and Kb1 must be related through Kw. That's all there is to the end of Chapter 6 and the Gen Chem Intro to Acid-Base Chemistry. Thanks a lot for listening.